Welcome back. Last episode, we built the technique of U substitution by running the chain rule backwards. It handles composite integrands beautifully. Anything with a function inside. A function structure where the derivative of the inside is also lying around. But composition is only one of the two structural ways to build a new function out of old ones. The other is multiplication. And the moment you write down a product of functions under an integral sign, x times e to the x, or x times cosine x, or even a lonely natural log of x, which we'll see is secretly a product, the chain rule has nothing to say. You need a different tool. You need the product rule run backwards. That tool is called integration by parts. The formula is short. The derivation is one line. The art, as always, is in choosing what to call u and what to call dv, and there's a beautiful little mnemonic called LIATE that gets it right almost every time. We'll cover the derivation, the LIATE heuristic, 4 examples in increasing order of slickness, finishing with Bernoulli's famous self-referential trick, and a tabular shortcut for when you have to do parts 3 or 4 times in a row. Quick gut check. The substitution rule, as we built it last time, eats integrands shaped like f of g of x times g prime of x, a composition next to the derivative of its inside. Almost all the integrals we did fit that mold by design. But look at these. Integral of x times e to the x, integral of x times cosine x, integral of the natural log of x all by itself, integral of e to the x times sine x. None of them is a composition. They're products. There is no inside function whose derivative is lying around. You can try substitution on these. You won't get anywhere. The shape isn't there. We need a different backwards running rule, and the only other big one in differential calculus is the product rule. Let's run the product rule backwards, explicitly. Take two differentiable functions u of x and v of x. The product rule says the derivative of u times v is u prime v plus uv prime. Old news from differential calculus. Now do the move we did with the chain rule last time, integrate both sides. The left side is the derivative of a product, so integrating it gives back the product itself, u of x times v of x by the fundamental theorem. The right side becomes the integral of u prime v plus the integral of uv prime. That's an identity. Now rearrange. Move one of the two integrals to the other side. Pick whichever one you like. By symmetry, it doesn't matter, but conventionally, we keep the uv prime on the left. So the integral of uv prime dx equals uv minus the integral of vu prime dx. That's the integration by parts formula, derived in one rearrangement from the product rule. No magic, just bookkeeping. Now write it in the form everybody uses. Using Leibniz's differentials, du for u prime, dx, and dv for v prime, dx, the identity collapses to integral of u, dv, equals uv, minus integral of v, du. That is the integration by parts formula. Memorize it. Tattoo it. 6 symbols on the right, 3 on the left, and it's the most useful equation in integration after substitution. Reading it, you're handed some integral. You split the integrand into 2 pieces. One piece you call u. The other, including the dx, you call dv. You differentiate u to get du. You integrate dv to get v. No constant of integration needed at this step. We'll absorb it at the end. And then the original integral equals u times v minus a new integral of v times du. The whole gamble is that the new integral, the integral of v du, is easier than the original. If it is, you win. If it's worse, you picked the split wrong. Back up and try again. So how do you split? 2 requirements. The piece you call u should be easy to differentiate. Ideally, something that gets simpler when you take its derivative. The piece you call dv should be easy to integrate. When both factors qualify, and they often do, there's a mnemonic that picks the right one essentially every time. It's called LIATE, and the letters stand for logarithmic, inverse trig, algebraic, trig, exponential. In an integrand with 2 factors from this list, the factor that comes earlier in LIATE becomes u. The other becomes dv. Why this order? Logarithms and inverse trig functions simplify dramatically when you differentiate them. The natural log of x becomes 1 over x, arctangent of x becomes 1 over quantity 1 plus x squared. Algebraic functions, meaning polynomials and rational functions, simplify gradually. X squared goes to 2x, goes to 2, goes to 0. Trig and exponential functions are essentially unchanged by differentiation. Sine becomes cosine, e to the x stays e to the x. So you want to differentiate the things that simplify and integrate the things that don't get worse. LIATE encodes that. It's not a theorem, it's a heuristic. 95% of textbook integration by parts problems obey it. First example, the cleanest one. Compute the integral of x times e to the x dx. Apply LIATE. The factor x is algebraic, that's the a. The factor e to the x is exponential, that's the ea comes before e, so x becomes u and e to the x, dx becomes dv. Now build the table. u equals x, so du equals dx. dv equals e to the x, dx, so v equals e to the x. The antiderivative of e to the x is itself, no constant needed at this stage. Plug into the formula. Integral equals uv minus integral of v du. That's x times e to the x minus the integral of e to the x times dx. The new integral is just the integral of e to the x dx, which is e to the x. So the whole thing is x e to the x minus e to the x plus the constant of integration. Always check. Differentiate x e to the x minus e to the x using the product rule. The derivative of x e to the x is e to the x plus x e to the x. The derivative of minus e to the x is minus e to the x. Sum e to the x plus x e to the x minus e to the x e to the x equals x e to the x. That's the original integrand. Notice what happened. The original integrand had two factors and we couldn't integrate it. After one application of parts, the new integral, the integral of e to the x dx, has one factor. The x that was making life hard has been differentiated away. That's the LIATE payoff. Differentiating the algebraic piece made it simpler. Second example, same flavor. Compute the integral of x times cosine x dx. LIATE again. X is algebraic, cosine x is trig. A before t, so u equals x and d, v equals cosine x, dx, de equals dx and v. The antiderivative of cosine x is sine x. Plug in. The integral of x times cosine x dx equals x sine x minus the integral of sine x dx. Now an antiderivative of sine x is minus cosine x. Be careful with the sign. The formula has a minus in front of the integral, and the antiderivative of sine also has a minus, two negatives. So we get x sine x minus open paren minus cosine x close paren plus c. The two minuses cancel, giving x sine x plus cosine x plus c. Differentiate to check. Derivative of x sine x by the product rule, sine x plus x cosine x. Derivative of cosine x is minus sine x. Sum sine x plus x cosine x minus sine x equals x cosine x. The original integrand. Done. Same pattern as before. We had a stubborn product. We differentiated the polynomial half, integrated the trig half, and the new integral was one factor lighter. Parts with the right LIE pick does this routinely. Third example. Compute the integral of the natural log of x dx. And here is the moment integration by parts earns its keep, because there is no obvious second factor. The trick is to invent one. Write the integrand as the natural log of x times 1. Now there are two factors, and LIAE has something to say. The natural log of x is logarithmic. L, the top of the list. Whatever the other factor is, L beats it. So u equals the natural log of x and dv equals 1 times dx, which is dx. Build the table. U equals the natural log of x, so du equals 1 over x dx. dv equals dx, so v equals x. The antiderivative of 1 is x. Apply the formula. Integral equals uv minus integral of v du. That's x times the natural log of x minus the integral of x times 1 over x dx. But x times 1 over x is just 1. So the new integral is the integral of 1 dx, which is x. Final answer, x times the natural log of x minus x plus c. Differentiate to check. Product rule on x times the natural log of x gives the natural log of x plus x times 1 over x, which is the natural log of x plus 1. Then minus the derivative of x, which is 1. Net, the natural log of x plus 1 minus 1 equals the natural log of x, the original integrand. This is a classic, almost everyone's first surprising integration by parts. The integrand looked unintegrable. Multiplying by 1 and applying parts turned it into a one-line problem. The same trick works for the integral of arctangent of x dx, the integral of arcsine of x dx, and any other lonely transcendental function that simplifies under differentiation. Fourth example, the slickest one in the whole technique. Compute the integral of e to the x times sine x dx. Call the whole thing capital I for short, we'll need to refer to it. Apply LIATE, trig before exponential, so u equals sine x and dv equals e to the x dx. Then du equals cosine x, dx, and v equals e to the x. First parts, capital I equals e to the x times sine x minus the integral of e to the x times cosine x dx. Notice, the new integral is not obviously easier than the old one. It's still a product of an exponential and a trig function. Have we made progress? Apply parts again to the new integral. Same logic, u equals cosine x, dv equals e to the x dx. So du equals minus sine x dx, and v equals e to the x. The integral of e to the x times cosine x dx becomes e to the x times cosine x minus the integral of e to the x times minus sine x dx, which is e to the x times cosine x plus the integral of e to the x times sine x dx, and that last integral is our original capital I. Now substitute back. Capital I equals e to the x times sine x minus, open paren, e to the x times cosine x plus capital I, close paren, which equals e to the x times sine x minus e to the x times cosine x minus capital I. Look what just happened. Capital I shows up on both sides of the equation. Move the right-hand capital I over to the left. 2 capital I equals e to the x times sine x minus e to the x times cosine x. Divide by 2, capital I equals quantity e to the x times sine x minus e to the x times cosine x over 2 plus c, or equivalently e to the x times quantity sine x minus cosine x over 2 plus c. We never explicitly computed an antiderivative. We bounced parts off itself twice, watched the original integral come home, and solve an algebraic equation for the unknown. This is the Bernoulli trick. Johann Bernoulli, who corresponded with Leibniz, popularized it in the 1690s. It works for any integrand of the form e to the ax times sine of bx or e to the ax times cosine of bx or sine of ax times cosine of bx. The integral becomes its own reflection in the formula, and a tiny bit of algebra finishes the job. One more thing, because it's a beautiful time saver, suppose you have to apply parts 3 or 4 times in a row. That happens when one factor is a polynomial of degree 2 or higher. Take the integral of x squared times e to the x dx. By LIATE, u equals x squared dv equals e to the x dx. After one round of parts, the new integral has x instead of x squared. After another round, it has the constant 2. After a third round, the polynomial has differentiated to 0 and the recursion stops. Writing all that out is a page of bookkeeping. The tabular method, sometimes called the DI method for differentiate, integrate, collapses it into one neat table. Here's the trick. Make 2 columns. The D column is the thing you differentiate. Start with x squared and keep differentiating, x squared 2x 2 0. The I column is the thing you'd integrate. Start with e to the x and keep integrating, which for e to the x is just e to the x every time. Then label the rows with alternating signs starting at plus plus minus plus minus. To read off the answer, take products along the diagonals, row 1d times row 2i, row 2d times row 3i, and so on, with the sign of the row you started from. So plus x squared times e to the x minus 2x times e to the x plus 2 times e to the x. Stop when d hits 0. Result, x squared times e to the x minus 2x times e to the x plus 2 e to the x plus c. You can factor out e to the x if you like, e to the x times quantity x squared minus 2x plus 2 plus c. 3 applications of parts collapsed into a table you can fill in 20 seconds. For anyone doing routine calculus, 2 problems, this is essential. A brief warning. The tabular method only works when the D column eventually hits 0, which means the thing in the D column has to be a polynomial. Polynomials differentiate down to 0 in finitely many steps. Exponentials and trig functions never do. So if you try to apply tabular to the integral of e to the x times sine x dx, you'd be in trouble. Sine x differentiates to cosine x, to minus sine x, to minus cosine x, to sine x again, a 4 cycle that repeats forever. The table would run forever and never terminate. In that case, fall back. Either apply parts twice manually and use Bernoulli's algebraic trick from example 4, or just use the standard formula. Integral of u dv equals uv minus integral of v du in long form. The tabular method is a shortcut for one specific shape of problem, polynomial times something easy to repeatedly integrate. Recognize when you're in that shape, use the shortcut, otherwise write it out. A moment of history. The integration by parts formula is, as we just saw, a one-line rearrangement of the product rule. So in some sense, Leibniz had it from the moment he wrote down differentials in the 1670s. His notation, the differential of uv equals u dv plus v du, is already begging to be rearranged. Once you write it that way, the integration by parts formula is sitting one step away, and the notation makes the step look like algebra rather than calculus. That's part of why Leibniz's notation won out over Newton's dot notation, which makes the same rearrangement look much weirder. The first systematic use of repeated integration by parts, applying it multiple times in sequence, which is what the tabular method automates, was Brooke-Taylor in 1715 in a treatise called Methodus Incrementorum Directa et Inversa. Yes, the same Taylor as Taylor's series. He did a great deal of foundational work on what's now called the calculus of finite differences, and integration by parts was one of his tools. And the Bernoulli trick, applying parts twice and solving algebraically, was popularized in the 1690s and 1700s by Johann Bernoulli, who corresponded extensively with Leibniz and his older brother Jakob. The Bernoullis were the great problem solvers of the generation right after Leibniz, and a lot of what's now standard in a Calculus 2 course traces back to their letters. Like substitution, integration by parts can fail. Here's the symptom. You apply parts, you get a new integral, the integral of v du, and it's harder than what you started with. Maybe the polynomial factor got worse, went up in degree instead of down. Maybe the trig got nastier. Whatever it is, the new problem isn't an improvement. The fix is mechanical. Swap u and dv and try again. The formula is symmetric. There are only two ways to split a product into u and dv, and if one fails, try the other. Usually one of them works. And one last thing, LIATE is a heuristic, not a theorem. Most of the time it picks the right u. Once in a while it doesn't, especially for unusual integrands. If LIATE says do this, and this makes the problem worse, override LIATE with the evidence in front of you. The mnemonic is a strong default, not a law of nature. Recap: integration by parts is the product rule running backwards. The formula, integral of u dv equals uv minus integral of v du. You split the integrand into two pieces, differentiate one, integrate the other, and rewrite the original integral in terms of a new and hopefully simpler one. LIATE picks the split: logarithmic, inverse trig, algebraic, trig, exponential. The factor that comes earlier in the list becomes u. The other becomes dv. We did 4 examples. X e to the x integrated to quantity x minus 1 times e to the x. X cosine x integrated to x sine x plus cosine x. The lonely natural log of x, treated as the natural log of x times 1, integrated to x times the natural log of x minus x, the classic. And e to the x times sine x, via Bernoulli's 2 rounds and solve trick, gave e to the x times quantity sine x minus cosine x over 2. For repeated parts where one factor is a polynomial, the tabular DI method collapses what would be 3 or 4 pages of computation into one little table. Use it when the D column terminates. Don't use it when it cycles. If parts makes the integral worse instead of better, swap u and dv and try again. The 2 ways to split a product are dual, and usually one of them works. Next episode, trigonometric integrals and trigonometric substitution. We'll tackle integrands full of sine and cosine at various powers, and we'll see how introducing a trig function on purpose can collapse the square root of quantity 1 minus x squared into something integrable. See you there! That's integration by parts. If this helped, hit like, drop a comment, and consider subscribing. It really does help the channel reach more learners. Post your favorite parts problem in the comments, especially one that needs Bernoulli's self-referential trick or 3 rounds of the tabular method. I read everything. Next episode, trigonometric integrals and trig substitution. Once you have substitution, parts, and trig sub under your belt, almost no integral in a first-year calculus course can resist you. See you in the next one. Substitution and parts together knock out most integrals in a first calculus course. The next great family of techniques specializes in trig, powers of sine and cosine, products with mismatched exponents, and the beautiful idea of trig substitution, where you introduce a trig function on purpose, just so a Pythagorean identity can collapse the square root of 1 minus x squared into cosine theta. If you want to see how in T the square root of 1 minus x squared x becomes the area of a circular segment without any geometry, subscribe. I'll see you there. If you got something out of this, please like the video, drop a comment with what clicked for you or what didn't, and subscribe for more educational videos. Every like, comment, and share helps push this work to more learners, which is what this channel is really about. Thanks for watching. See you in the next one.